If our depth function is 0.05 t squared minus 5t plus 100, then the vertex is at the negative b over 2a point, which we calculate to be negative, b is negative 5, a is 0.05, so negative b over 2a is negative of negative 5 divided by 2 times 0.05, which is 50. And that's the time at which this depth model will reach its vertex. And what's the significance of that? Well, first let's calculate the y-coordinate of the vertex. We just evaluate y when t is 50. So we plug 50 in for t. We get negative 37.5. So our graph for the depth from the point where it's from the t equals 0 point up to the point where we reach the vertex is this. The domain of the function is only from t equals 0 to t equals 50. We stop at the vertex because, of course, the container doesn't refill. Now, we want to use this function to answer a couple of questions about the average rate of change. What's the average rate of change of y with respect to t, which is the average rate of change of depth with respect to time between t equals 10 and t equals 20? Okay, well, y of 10 is 55, y of 20 is 20. And you can evaluate for this function and verify that I did this calculation correctly or figure out that I didn't. This gives us 2 points on the graph. The point where t is 10 and y is 55, that's the point 10, 55. Of course our t-axis is here, and our y-axis is here. And the point where t equals 20 and y equals 20. So that's the point 20, 20. The average rate of change from here to here, well, is the slope of the fundamental triangle. Slope of the segment from here to here, which is 10 divided by negative, well, I'm sorry, the rise, negative 35, divided by the run, 10, which is negative 3.5. This actually has a meaning. If y is in centimeters and x is in seconds, this would be negative 35 centimeters over 10 seconds, which is negative 3.5 centimeters per second. And this is how fast, on the average, the water is descending between the t equals 10 second and t equals 20 second mark. Between t equals 20 and t equals 30, well, the interpretation's again going to be the same. The slope is going to be the number of centimeters change in the depth, and the run, let's say the slope, the rise is going to be the number of centimeters change in the depth. The run is going to be, again, 10 seconds. And the average rate of change is going to be in centimeters per second. Well, at t equals 20, we get the point 20, 20, which we already had. At t equals 30, we can calculate, plug into the equation. We get, I believe, negative 5 for the y-coordinates. We get the point 30, negative 5. So the rise from 20 to 30, the run is 10. The rise is negative 25. The average rate of change is negative 25 over 10, which is negative 2.5, meaning depth changes at the average rate of negative 2.5 centimeters per second between t equals 20 seconds, t equals 30 seconds. And then from t equal 30 to t equal 4, we get these 2 points, and the average rate of change is negative 1.5. Now, one thing we see is that on these equal intervals, these 10-second intervals, the average rate of change changes from negative 3.5 to negative 2.5, and then from negative 2.5 to negative 1.5. The change from here to here is the same as the change from here to here. And that's a characteristic that can be proven for a quadratic function. Okay, well, there are other questions we can ask of this model. These average rates of change are very important. We'll see a little bit more about how important with respect to our project. Another question we could answer for this function, though, is when is the depth 10? How do we calculate when the depth is 10? Well, y is the depth. If the depth is 10, then y is 10. And if y is 10, then this expression for y of t has to be equal to 10. And this can be solved using the quadratic formula. We will get a solution because, as we can see from our numbers here, depths are 55, and then we have a depth of 20, and then we have a new depth of negative 5. So depth clearly crosses or passes the 10 centimeter mark. Now, what's the velocity of this thing when the depth is 70? Well, we're given in the statement of the problem that the velocity function for y equals at squared plus bt plus c, the velocity function, and we've calculated here average velocities. Okay, this is the average velocity of the water surface as it descends between the 55 centimeter and 20 centimeter mark. This is the average velocity between the 20 and the 20 and negative 5 centimeter mark, and this is the average velocity between negative 5 centimeters and negative 20 centimeters. The velocity can be calculated by this function. We identify A, B, and C. We don't need C, but we plug in the value of A and the value of B, we get our velocity function. Well, we know that for this given function, A is 0.05, B is negative 5. So 2AT plus B becomes 2 times 0.05T minus 5. 0.1T minus 5, there's our velocity function. And this is just indicating how we got the A and B values. Here's our y equals 0.05T squared minus 5T plus 100. 0.05 is the A, negative 5 is the B. We plug that into this function, and here we have it. Here's our function. We could, just a little extra, figure out what the, well, let's see, we're going from the 55 centimeter to the 20 centimeter mark here. Halfway between those is the 37.5 centimeter mark. Okay, and what's the velocity? And halfway between 10 seconds and 20 seconds, even better, is 15 seconds. What's the velocity at 15 seconds? That's negative 3.5. What's the average velocity between 10 and 20 seconds? Negative 3.5. So the average velocity on this interval is the same as the velocity at the midpoint time of that interval. You could check that the same thing is true here. This would predict that at halfway between 20 seconds and 30 seconds is 25 seconds. So if we evaluate this at 25, t equals 25, you should get negative 2.5. And then an analogous thing here. Okay, now how do we find the velocity when the depth is 70? It's just a little aside here, but it's kind of a significant property of quadratic functions. Okay, what's the velocity when the depth is 70? How do we answer that question? We don't have a function that tells us the velocity when we know the depth. Well, what we do have is this function that'll tell us the time when we know the depth. So we can find the time when the depth is 70 by solving this equation for t. And then that gives us a t to plug into the v of t function to get the velocity when the depth is 70.